In this section, we're going to learn about creating new sequences from existing sequences. The idea of a subsequence of a sequence is that you take an existing sequence and just skip some terms to create the new sequence. The most important feature is that the order of the terms remains unchanged. Consider the following sequence. There are two obvious subsequences we might try to create from this by taking every other term. By starting from the first term and taking every other term, we get a constant sequence. By starting from the second term, we get a decreasing sequence of the form 1 over n. But we don't even need to follow a meaningful pattern. The important thing is that we do not rearrange the terms. In order to discuss this idea in general, we need to come up with a notation to indicate the sequence and the subsequence. There are a number of ways to look at it, but we will focus on the subscripts. Definition. Suppose S sub n is a sequence. A subsequence of S sub n is a sequence of the form S sub n sub k, where n sub k is a strictly increasing sequence of natural numbers. In the definition, we have explicitly indicated the indexing variable to avoid confusion. The original sequence is indexed by the letter n, and the subsequence is indexed by k. Let's take a closer look at what this means. Let's say we want a subsequence that starts from the first term and takes every other term. That will look like this. Here's the original sequence, and here's us taking every other term starting from the first one. The first term of the subsequence has index k equals 1 and corresponds to n sub 1 equals 1. The second term of the subsequence has index k equals 2 and corresponds to n sub 2 equals 3. The 3 comes from the fact that this is the third term of the original sequence. This pattern will continue for the rest of the terms of the subsequence. You can think of the n sub k as being the sequence that tells you which terms to include. It's important that the n sub k are strictly increasing so that you will never repeat a term and that you can never go backwards. Since any given sequence has infinitely many subsequences, this concept opens the door for us to discover new features. For example, if we return to the original example, we started with a sequence that didn't converge, but we saw that there were at least two subsequences that not only converge, but converge to different limits. We're going to take a look at a quick theorem about sequences and their subsequences. Theorem. If the sequence S sub n converges, then every subsequence converges to the same limit. The key to this proof is recognizing that the subsequence runs ahead of the sequence. This happens because the subsequence can sometimes skip terms but can never go backwards. Let's take another look at the every other term example. Notice the second term of the subsequence is ahead of the second term of the original sequence, and the third term of the subsequence is ahead of the third term of the original sequence, and so on. In general, we can say that n sub k is greater than or equal to k for all k. Since the original sequence S sub n converges, for any epsilon greater than 0, there is a point at which all the terms are within epsilon of the limit. But the subsequence reaches that point long before the original sequence does, so the subsequence will also be close to the limit. Here's the formal proof. Let S be the limit of S sub n, and let epsilon be greater than 0. Then there exists a capital N such that n greater than capital N implies the absolute value of S minus S sub n is less than epsilon. Suppose k is greater than n. Then since n sub k is greater than or equal to k, we have that n sub k is greater than capital N as well. This means that the absolute value of S sub n sub k minus S is less than epsilon. To fully appreciate just how complex sequences and subsequences can be, we are now going to consider a sequence that contains every single rational number infinitely many times and has subsequences that converge to every single real number. Consider the following grid of values. Notice that every single rational number is listed somewhere in this grid because we have all possible numerators going left to right and all possible denominators going down. We are going to create a sequence by starting at 0 and moving back and forth along the indicated path. By doing this, we will eventually get to every single rational number. In fact, we will get every single rational number infinitely many times because there are infinitely many representations of every single rational number. This example gives us a glimpse into the level of complexity that can be involved when working with sequences. Mathematicians sometimes call examples like these pathological examples because the result is counterintuitive. It seems strange that a function indexed by the natural numbers could actually cover the entire set of rational numbers infinitely many times, but it turns out to be true.